Okay, now that we've meshed our geometry, let's move forward with the rest of the simulation. So, moving on, I'd like to go to the property module and define a material. So the material I came up with in a paper, um, which was about stress analysis of the pressure vessels, was SUS 316. So I'm gonna define it here. So on the property module, click on create material, and then a window pops up. You can name the material whatever you want. So I'd rather call it SUS 316. And I'd like to define the elastic properties of the material. So go to mechanical, under elasticity, select elastic. Now, the Poisson's ratio of the material is 0.3. So I just enter 0.3 because this is a dimensionless unit. It's dimensionless quantity. Okay? But the Young's modulus, if you recall the previous video, I said we have to assume our own measurement system because Abacus does not have a well defined built in system of measurements like other softwares. So you have to come up with your own measurements and be consistent throughout your simulations. So, um, I mean, you can check this by going to Tools, Query, and check a random distance on your geometry. So I'd rather click on distance and get the distance from this point to this point. So the distance that is showing is roughly 762. But since I don't know exactly whether it's in meters, millimeters, or centimeters, I have to assume something. So since this is a hypothetical case, I'd like to assume all the dimensions are in millimeters. So 762 millimeters. Now, if I assume my force is being applied in newtons, then the Young's modulus that I enter here should be in megapascals because newtons over millimeters squared. Okay, so the Young's modulus of the material is 193 gigapascals. If we convert it to megapascals, it would be 193,000 megapascals or newtons per millimeter squared. And now I have my material properties defined. Now I hit OK. If you go to the material manager, you can see that you have your material defined. Okay. Now I have to define a section, so I hit this button, create section. By default, you can see that it's the category selected as solid and the type selected as homogeneous. And I'd like to stick with that. So I hit continue. The material I want to use for this section is the material I just defined, SUS 316. Everything is good. I don't need to change anything. So I just hit OK. And you can see that the section is well defined. Now I have to assign the section to the whole geometry. So click on this icon, assign section. Now Abacus usually prompts to create sets, which is really helpful for some cases. But here I'd rather not define it for the sake of simplicity. So I check this create set option off, and then I select the whole geometry, hit done. Now this a window pops up asking me which section I want to assign. So since I only have one section, and it's clicked on it, so I don't have to change anything. I just check it's solid homogeneous. The material is SUS 316. Everything is okay, so I just hit OK. And after you assign the section, you can see that the whole geometry is turned green, which tells me that I'm on the right path. Okay, so the next step, I'd like to assemble my model. And um, no matter how many parts you're dealing with for your model, in Abacus you always have to assemble. So in your assembly module, you need to click on this icon, Create Instance. So click on it. Since you only have one part, it shows up and is highlighted. Um, and you don't have to do anything else. Just hit OK. Now you have your assembly. So moving on, now I need to define a step. So I go to the step module and I click on create step. So Abacus always by default has an initial step, and that you cannot change. It's determined by the software. So you can name your step. So it's by default named step 1. I'd like to leave it as it is. And in Abacus, there are many types of steps depending on the physics of your problem, the type of loading. For instance, here I'd like to apply static loading, static pressure. So the step that I need to define is static general, which is selected by default. So don't change anything, hit continue. And since this is a static loading, the loading is not dynamic, it's not time dependent. You don't really need to change anything in terms of the time period and incrementation. So leave the setting as it is. You can consider the nonlinear geometry effects or not. For this case, I don't think it would make a big difference, so just check it off and hit OK. And if you go to the Field Output Manager, you can see that Abacus has already predefined something and requested some outputs. If you click Edit, you can see in details. So these are the variables usually that Abacus calls when doing such simulations. The stresses, the strains, displacements, forces, reaction forces, contact forces. And since we're mostly interested in the stresses and strains, which is already called, I don't have to change the settings, so I just hit OK. Just wanted to show you. And sometimes we want to define some history outputs depending on the problem we're dealing with, which is by default requested in Abacus. So if you hit Edit, you can see that some variables are defined here. But sometimes you need to call different history outputs, which is not the case for this simulation. Okay, now moving on to the next step. So the next step usually should be interaction, but since I'm only dealing with one geometry and one part, I don't have to define any interactions. Interactions are handy when you're dealing with multiple geometries or multiple parts. Sometimes you want to fix 2 or more geometries together. For that, you need to define an interaction. You need to define a tie contact. Or sometimes you want to load one geometry on another geometry. So for that, you need to define a contact, mechanical contact. So this is not the case for the simulation. So next, we need to go to the load module to apply our boundary conditions and loading conditions. So first, I'd like to fix the bottom surfaces of the supports of my pressure vessel. So for doing that, I need to go to this icon, Create Boundary Condition. Click, and then a window pops up. The category should be mechanical, symmetry, anti-symmetry, and caster. And then I hit continue. And then I manually select these 2 bottom surfaces. So I click one surface, And in order to click both surfaces, when doing the second one, you need to hold Shift and then select the second one, and then hit done. And then another window pops up saying which type of boundary condition you want to apply. So I'd like to fix all rotations and all translations. So I click on Encaster and hit OK. And now I'd like to apply an internal pressure to the internal walls of my geometry. So for that, I would go to the Create Load button, click on it, and I need to go to pressure. So make sure pressure is selected. Make sure you're in step 1, not the initial step, and hit continue. Now I have to manually select all the internal surfaces. So let's do this. Okay. Some surfaces might be out of reach, so let's work our way through to find these surfaces. Okay, once you're done selecting all the surfaces, just hit done. And then the software is asking for the magnitude of the pressure, of the internal pressure. So let's enter 5, which represents 5 megapascals of pressure, and hit OK. Now let's check whether all the internal surfaces of the geometry selected. So for that, open Load Manager, hit Edit. You should be able to see better here what's happening. You can see a wireframe representation also. I think this surface is not selected. This surface as well. So how do I select those two surfaces that are missing? So I go back to the shaded view and click on Remove Selected. Make sure you're selected on cells. I want to hide some partitions, so let's hide this partition and this partition first. And then hit done, and then edit again. Okay, now these surfaces are not selected, so let's select these. So please click on this icon where it says Edit Region. Now hold Shift, click on this surface, click on this surface, and hit done. Okay, now let's show everything once again, and let's double check whether everything is selected. And you can see that all the internal surfaces of the geometry is selected. Now let's go back. So now we have pretty much defined everything that we need for the simulation. So next step, since we've already meshed, I'll just skip this step and go directly to the job module. Now we have to define the job in order to perform the simulation. So click on Create Job, and I'm doing this, dealing with this model. Sometimes in an Abaqus file, you're dealing with several models, so make sure you're clicked on the right model and hit continue. And a window pops up. In order to speed up my simulation, I'd like to use parallelization, so click on parallelization and check use multiple processors on. Maybe use 4 You can use more, of course, but I'd rather stick with 4 cores. Hit OK, and then you can go to Job Manager, and you can see that your job is defined. Now all you have to do is to hit Submit. Since I previously ran a job with the same name, it's asking me to overwrite, which is not a big deal. So I hit OK. And if you click on Monitor, you can monitor the job while it's running. This is handy for heavier simulations. Now I have to wait for the simulation to finish. So once complete, you should be seeing completed under the status. Now the job is complete, so close the monitor window and hit results, and you'll be prompted to the visualization module. And you can see the deformed shape of the pressure vessel, but this is really exaggerated. In order to see the actual deformation, you need to go to this button, Common Options, click on it. You can see that the deformation is scaled up by a factor of 72. We don't need that. So click on Uniform, enter 1, hit Apply. Now you can see the real amount of deformation. It's very small. Now, if you click on this button, you can see different variables, different mechanical responses, such as stress, strain, and so on. For instance, right now I'm clicked on stress, and I can see the von Mises stress. Now I can see the maximum principal stress, the normal stress components in the stress tensor, as well as the shear components. And that's pretty much it with the simulation.